Hello everyone. In this video, I'm going to discuss how to solve the related rate problems. If you recall, in the previous video, we did some review of the things that we need to know in order to solve the related rate problems. So now I'm going to do this example, and after doing this example, we will discuss the strategy or the step that we learned from this example that we're going to use for solving any kind of related rate problems. Let's start. Take a moment. If you want, you can pause this video and read this problem carefully. So in this problem, we are given a metal plate that is being heated and it causes area to increase. So we have a dimension x and a dimension y. So dimension x is increasing at a rate of zero point 0.1 millimeter per minute, and dimension y is increasing at a rate of 0.2 millimeter per minute. So we need to find how fast is the area increasing when x is 10 centimeters and y is 20 centimeters. So whenever we read a problem, first step is we want to figure out what is given and what is unknown. So the given rates are, so change in x with respect to time. So dimension x is increasing at a rate of zero point 0.1 millimeter per minute, and it tells us that it is increasing. So that's why we are using positive 0.1. And another thing we notice that x is given 10 centimeters. So centimeter and millimeter. So what we want to do is we want to convert everything in terms of consistent units. So let's convert everything in terms of centimeters. So zero point 0.1 millimeter per minute means 0.01 centimeter per minute. Also, we are given the change in y. So y is also increasing at a rate of 0.2 millimeter per minute. So again, it's increasing positive value, and this is equal to 0.02 centimeter per minute. So now the question arises, what we want. So we want, or what is unknown. So we want to find how fast is the area increasing. So dA over dt. So rate of change of area, and we want to figure this out when x is 10 centimeters and y is 20 centimeters. So far we have just done one step. So we read the problem and we just wrote what is given and what we need to find. Now, since we are interested in finding the rate of change of area, or how fast is the area increasing, it means we need to find equation that links our area with our known values. So we're going to find a relationship between area and in terms of x and y. So how can we find this area? So I'm just going to divide this diagram into two parts. So one part and second part. So we can try to write the area of first part plus area of second part. So that will give us the total area. So in this case, if we try to write area of our shape 1, so this dimension would be, so we have y plus x. So this would be y plus x, and the other side is y. So for number 1, we have y times y plus x. So that is our area of portion 1. Similarly, for the other one, we have x times x, which is x square, because this side is x and also this width is x. So plus x square. So our equation becomes y square plus xy plus x square. And this is our area. So area is in terms of x and y, so y square plus xy plus x square. So now our goal is to find dA over dt. So we're going to take the derivative of area equation with respect to time. Thus in our third step, we're going to take the derivative and we're going to get our related rate equation. So take derivative with respect to t on both sides. So dA over dt is equals to, so we are taking the derivative of each term with respect to time. And we notice that, so derivative of y square with respect to t, so here we have variable t, so this is y, so we have different variables, so we have to apply the chain rule. So 2y dy over dt, and for any x and y terms which are in the product, we're going to use our product rule, so u times v. So use your product rule for this mixed term. So that will give us x added as it is derivative of y with respect to t plus y as it is derivative of x with respect to t. And for the last one, again, we're going to use the power rule. So 2x dx over dt. So let's combine the x terms together. So bring the x dx over dt terms together. So we get dA over dt is equal to, so dx over dt. So here we have, so this term and the last two terms are the dx over dt terms. So we get inside y plus 2x. Similarly, we're going to combine the terms containing dy over dt. So this one and this one. So these two terms together. So dy over dt is common factor. So we get 2y plus x. So this is our final related rate equation. So once you have your final related rate equation, so now is a good time to plug in all the known values and solve for unknown. So in the beginning of the problem, we saw that we are given the rate of change of x, rate of change of y, and also x and y values. So I'm going to plug in these values in our final related rate equation so we can find the change in area with respect to time. So dx over dt is 0.01 centimeter per minute. So y is 20 and 2 times x is 10 plus dy over dt is 0.02 and 2y means 2 times 20 plus x means plus 10. And when we solve this, so overall we get 1.4 square centimeter per minute. So area is increasing at this rate. Or if you prefer, you can write your answer in terms of square millimeters. So mm square over, so 140 square millimeters per minute. So this is the rate of change of area. So area is increasing at this rate when x is 10 and y is 20 centimeters. Hence we solved the problem and we figured out what we were looking for. So let's just review this and do a recap of our strategy for solving the related rate problems. So read the problem carefully and identify the given things and the unknown rate for the problem. Second step is find an equation that links all the rates and variables together. Third step is take the derivative with respect to time. So, and don't forget to use the chain rule. So take the derivative of the equation that you just found in step 2. And the last step is substitute the given values and the given rates and solve for the unknown rate. I would like to take this opportunity to address to the common errors that students usually make. So the one most common error that students make is forgetting to take the derivative with respect to t. And thus it results into the losing one of the terms like dx over dt or dy over dt. And another mistake is people tend to substitute the values too early. So do not substitute the values too early. Wait till end until you get your final related rate equation. Only then you substitute the values. This will result in No errors. So as long as you follow all these four magic steps carefully, you will be able to ace any related rate problems. I hope that makes sense. In the next video, I will do some more complicated related rate problems. So if you are interested, please watch that video as well. See you next time.